So, welcome back to another nuclear chemistry seminar, and today I would like to talk a bit about the very exotic elements Promethium and Technetium, and what's the plan for today. So, first of all, they are unstable. This is why they are popular amongst nuclear chemists. But why aren't they stable? It's not going to be a very in-depth explanation, but rather to throw in Mattau's rule so that everybody knows about. And I would then like to quickly mention why they're important for chemistry and how do we get them to do research on them and why is this whole topic even relevant. So first of all, Mattau's rule, to summarize it quickly, there are no stable isobar neighbors. For example, we have the 66 isobar. Since zinc 66 is stable, copper 66 can't be stable. And there can only be one stable isotope for an uneven isobar. For example, the 65 isobar, which is uneven. 65 is an uneven number. You have the copper 65 as the only stable nuclide on this isobar. However, you can have two stable nuclides on a even isobar. For example, we have the nickel and the zinc 64 as the two stable nuclides on this isobar. However, they are two, but they are not neighbors. So they are separated by copper 64. Why is that? Well, there is a pairing term when you look at the Bethe-Weizsäcker formula, which the last part, the pairing term, gets positive if you have two even nucleon numbers, so an even proton number and an even neutron number, which will then turn this term positive, leading to an increase in stability of this nuclide. But you can also have an even nucleon number by having two uneven protons and a neutron uneven number, which will then add to an even nucleon number. And this is the case for copper 64. Copper 64 is a UU nucleus with 29 protons and 35 neutrons. But UU, so uneven proton number and uneven neutron number, will make the last term at the Bethe-Weizsäcker formula negative, leading to decreased stability of the nucleus, meaning that this increase due to a positive pairing term can make a nucleus, for example, let's say zinc, stable even though it would have a relatively high proton excess. But since we have the pairing term, it makes this one stable. So now we know that on an uneven isobar, we can only have one stable nucleus, and on an even isobar, we can have two stable nuclei, but they can't be neighbors. Looking at the technetium isobar, we have the 99 line, which ruthenium occupies the only stable nuclide for this 99 isobar. For the 98, we have molybdenum and ruthenium, therefore leaving no space for technetium, which makes sense because technetium 98 is a UU nucleus because technetium is element number 43, so therefore it has an uneven number of protons, and to get to a even nucleon number, it has to have a uneven neutron number, meaning that this is a UU nucleus. This is a UG nucleus, and this is again a UU nucleus. Looking at the 147 line, we have promethium again as element number 61. It has to have at least one uneven number, the proton number. And in the case of the 146 line, it also has an uneven neutron number, meaning that this is again a UU nucleus. I would quickly like to mention that there are no stable isotopes on the 147 line, whereas on the 99 line, we have at least ruthenium as the only stable nuclide. But looking at samarium, it is primordial, so it is also radioactive. There are no stable isotopes on the 147 isobar, which I think is overlooked most of the time. I think this is quite exciting. So, coming to chemistry. Well, if you look at the periodic table, you can see group 7 includes manganese, blank, and rhenium, and then again blank. I'm just going to ignore borium. But if you want to investigate, for example, the tetraoxo ions or anions, you have the potassium permanganate as the most popular oxidizing agent, and then you have a hole, because technetium chemistry is quite rare, and then you have rhenium. So you only have two data points to do research on the whole group 7 chemistry, which is not that much. So you would have to include technetium to at least be able to draw a curve, because you can only draw a straight line with 2 points, but you can only draw a curve with at least 3 points, or more would be better, but borium is out of question. But there's even another trend. For example, these are also isoelectronic. The chromate, the pertechnetate, and the osmium tetroxide. These are all so-called tetraoxo compounds, and since we work with pertechnetate as a tetraoxo compound, I wanted to mention this example, but you can also look at the, for example, carbonyls. And yeah, technetium is right in the middle, and since it's so rare, there's a huge lack of chemistry when it comes to this trend and this trend because of lacking technetium chemistry. So how do we get them? Both are fission products, mainly the technetium-99 and the promethium-147 through the isobaric chain yield. Meaning that since you do nuclear fission from a very neutron-rich isotope like uranium-235 or the compound uranium-236 nucleus, it splits into two very neutron-rich fission fragments, which will then do beta-minus decay to get rid of this neutron excess and will then go up the isobaric chain into the value of beta stability, and then they can produce technetium-99 or promethium-147. Because if we go back a bit, we can see that if a nucleus of mass 100 were to be formed, it would then decay beta-minus decay up to molybdenum 100 and would then stop, because molybdenum is quite stable, therefore it can't form the technetium 100 because this one doesn't do beta-minus decay. So the only way to get technetium 100 is to have a exact perfect fission that leads directly into technetium forming a direct fission product. But this is really unlikely because, well, the chances of this happening is quite low. But for technetium-99, you have the whole 99 line. So if molybdenum-99 were to be formed, it would produce it, niobium-99, zirconium-99, yttrium-99, and so on. They will all lead into technetium having a huge amount of technetium being produced. And to get that with numbers, we have 6.13% of all fission products ending up into technetium-99, whereas we have about 2.2 something percent for uranium-235 fission when it comes to promethium. As a quick side note, all fission yield will then eventually be added to above 200%. So it's not 6% out of, in general, 100, but of 200% view, because you make out of one atom 2 fission fragments, therefore having a yield of 200%. So promethium is among the lanthanides. It's on the heavy branch, so this one. And you get fission products of the lanthanides up to samarium. Europium is with less than 1%, and all of the heavy lanthanides like dysprosium or holmium, they can be neglected for all practical purposes because they are produced in very low quantities. But the first ones, lanthanum up to samarium and including promethium, have a very high chain yield on the heavy fission branch. So after nuclear fission, we have this whole goo of transactinides and fission products and still unburned uranium. But how do we get these two elements out of them to get these two samples to do chemistry with? Well, there's a scheme for technetium. It's quite detailed. I copied that from the technetium book, and I also made a other seminar about this, so have fun looking at this. And for example, I had to look up the purification of promethium from the fission products, and you would then first precipitate out as a oxalate, then treat this precipitate with acid to redissolve it again. Then you can precipitate, for example, serum as iodate, whereas the later lanthanides, which are not that important, will stay in solution if you add sodium carbonate. And you can then treat it with acid and elute it over a cation exchange with 5% citrate solution, because promethium is really hard to isolate, whereas technetium is its own element. But the lanthanides have the characteristics of being chemically very similar, so isolating promethium from the fission products is much harder than isolating technetium from all of the other fission products, because technetium is its own element, whereas most other elements nearby have quite different chemistry, whereas promethium really needs a cation exchanger to get it out of the solution from samarium and neodymium, for example. But why bother? Well, technetium, of course, everybody knows the medical applications from technetium, but this is not really where we get our technetium. We get it from molybdenum, which is a fission product, molybdenum-99. So, as I said before, fundamental research. Of course, we want to know our chemistry. We want to have more proof that the system, the periodic system, is correct the way it is. And we want to, for example, predict the chemistry of boron after knowing the chemistry of the other group 7 elements like manganese and rhenium. And if we were to leave out technetium, this would be very poor data for boron chemistry because we really need to see trends and therefore we need to include the third element. And when it comes to promethium, we should look at the nuclear applications of lanthanides because they have, for some reason, really high cross-section when it comes to neutrons. So all of the lanthanide chemistry, which includes promethium chemistry, has to be understood to fully know what they're doing inside of their reactor. Therefore, we have this really high purity promethium-147 chloride solution to, for example, investigate the behavior of ion exchanger to further investigate the purification of fission products or other lanthanides. And it includes promethium. And since they have really high fission yield and a quite long half-life, technetium 210,000 years and promethium-147 above 2 years, they can't be completely neglected when it comes to nuclear waste management. So we have to know their chemistry because the nuclear waste can also do chemistry, which we have to understand. And if we don't, and it gets into the environment, technetium is a bitch. I'm not sorry, but since it's negatively charged, it's highly mobile as the pertechnetate ion, and still the insoluble compound, the technetium dioxide, which is analog to magnesium dioxide, is still somewhat water soluble. Technetium in the dioxide form can still be in aqueous solution with a activity concentration of 150 becquerels per liter, which is not to be neglected. If we look at this scheme, which shows us the various oxidation states, we can clearly see that at normal environmental pH values, we have either the technetium dioxide, so the technetium 4+, or the technetium 7+ as the highly mobile pertechnetate ion. As I said before, technetium is a fission product, so you want to know what the chemistry of the fission product with the material of the vessel, which it contains the waste material, is all about. So we have to know technetium chemistry in presence of, for example, other waste products and with the iron and chromium and carbon of the vessel material. Before we end this seminar, I would quickly like to show you this graphic, which roughly shows you the activity against time in seconds or days, hours, and years. And as we can see, for example, strontium-90 with a half-life of 30 years, 10 times 30 years, after 300 years, it's roughly gone. Yeah, as you can see here. So after 300 years, most of our fission products will be decayed away. For example, iodine-131 will decay in less than 1 year. But the technetium-99 with a half-life of 210,000 years, which is more long-lived than some of the other plutonium isotopes, which are highly toxic, will stay in there for pretty much forever. So after 30,000 years, we don't even make a dent into the technetium-99 activity from our waste material. Meaning that the technetium-99 chemistry is really important to understand the also highly mobile waste material that we create when doing nuclear fission. With that being said, thank you for attention and goodbye!